Cn, that's going to be the number of vertices. And they should be distinguishable. And what we're going to do with these trees, oh, and another convention that I'm going to use, which will be important, is I'm often just going to use T just for the vertex set. So usually when I write down T, I just mean the vertices. I'm not going to use V of T or something more cumbersome. I'm just going to write T. So the things that we're interested in are what are called increasing labelings. So an increasing labeling. Well, it's going to be a bijection, call it L, say, L for labeling, between the vertices of T and the numbers 1 through n. Right, so those are the labels. And what makes it increasing is that if I've got a vertex V, which has a child W, then the label that I give to V is smaller than the label that I give to W, right? So as you go out from the root, your labels are going to get larger. Okay. So, quick example, let's put it over here. Suppose I have this tree, and I'll put my roots on top, opposite to the biological norm, but consistent with the way computer scientists like to do things. So my roots at the top there. So what are the labelings going to look like? Well, clearly the root, because it's above everything, has got to get the smallest label of 1. And then if you think about it for a second, I can choose any of the numbers 2 through 4 to go on this vertex. And once I've done that, the rest of it's going to be determined, because I've got to put the other 2 labels that are left out down here in increasing order. So I could put 2 there, which would leave 3 and 4 on the other side. I could put 3 there, which would leave 2 and 4 on the other side. Or I could put 4 there, which would leave 2 and 3 on the other side. So there are the increasing labels. And we're going to use the notation F super T. That's going to be the number of such. So here we have just computed by hand that I have 3 possible labels for that particular tree. Is this clear? This is the start of the talk. If you're lost already, then it's not going to make much sense later on. Okay, so what we'd like, of course, is to have some formula that would compute f of t for us without actually having to go through and calculate each one of these individually. And there is such a famous formula, so let me tell you about this. And this is where these things called hook lengths come in. So, hook length of a vertex V in my tree is denoted H sub V, and it's just the number of descendants. So everything, and we include V in this, everything from V on down. Okay. So, famous theorem is the theorem of Donald Knuth's. Formula. And it says that if T has n vertices, so I'll use vertical bars to denote the cardinality of the set. If T this has n vertices, then there's a very simple and beautiful formula for the number of increasing labelings. It's n factorial over the product of all the hook lengths. Couldn't ask for something nicer than that. So for example, here, what do the hook lengths look like? I'll put them in nice pink color. So this is not an increasing labeling. This is going to be the hook lengths. So, well, for the root, everything is below the root, all 4 vertices. So that has a hook length of 4. This vertex, as for any leaf, there's only itself below it. So there's going to be 1 there, and there's 2 things below this. And lo and behold, if we take n factorial over this product, we've got 4 factorial over 4 times 2 times 1 squared. Everything cancels out in from the top except for the 3. And lo and behold, they're identical. QED. No, not quite. But at least, hopefully, this gives you some hope that this is a true statement. So now let me give you a little bit of history at this juncture. So the idea of giving probabilistic proofs of formulas that involve hook lengths actually goes back to Curtis Green, Albert Nienhuis, and Herbert Wilf, who gave a probabilistic proof of a formula very much like this, but for a different class of objects called standard Young tableau. And I myself later got into the act with things called shifted Young tableau and so forth and so on. But what I'm going to show you today is a probabilistic proof of a new type of formula, also involving hook lengths, but not this particular one. So to describe this new formula, let's see, where are we going? This one. We don't need this example anymore. We need a little bit of notation. So let's script B of n be the set of binary trees C on n vertices. So by binary here, what I mean is that for each vertex, if you look at its children, it either has a child on the left, a child on the right, both children, or neither. And we're going to let script L sub n be the set of labelings of such binary trees. Again, quick example just to make sure that we're on the same planet. What does B3 look like? Okay, so if we've got 3 vertices to play with, you could always start from the root and go to the left. That's my own political preference. Or you could start out going to the left and then go to the right. Or the root could have 2 children, a left child and a right child. Or then it could go right and then left, or it could go right and then right. George W. Bush tree. Okay, so that's what the binary trees look like. And what about their labelings? Well, most of these trees, there's only one way to label them, right? Because they're essentially paths down from the root. So for example, for this tree, I don't have any choice. I got to do it this way. Similarly for this tree, we do have a couple of choices, right? We can put the 2 on the left and the 3 on the right, or vice versa. And then the rest, again, we have no choice. Okay, so that's what that one looks like. So here's the formula that let's see, if I'm about here, is that, you're okay with that? Am I okay with it? Can I reach that high? Okay, so here's the theorem that we're after. This is a theorem by Guo-Nu Han. Paper of his, what, 2008. And it says the following. For any n, let's look at the following sum. I sum over all binary trees on n vertices the following product. Product over all vertices of t, 1 over the hook length times 2 to the hook length minus 1. And if you add up all of these nasty products and cancellation occurs, you will miraculously come up with 1 over n factorial. So this is a bit of an amazing result. This simplifies so nicely. Now, Han's proof of this was purely algebraic.